Formation of solar system is a mystery. It is said that solar system might have formed due to accumulation of gases and dust particles present between the stars. It is thought that solar system is more than 4.5 billion years old. The sun, the moon were always center of attraction of the ancient astronomers. The movement of stars and the unknown bodies in the sky gave rise to a new science called astronomy. Information about planetary motion, speed of planets, and period of planets. The path traced by the motion of the planets was given by Johannes Kepler, a German astronomer and mathematician. Johannes Kepler was born in a precarious family on December 27, 1571 in Holy Roman Empire of German nationality. From childhood, Kepler had strong passion in observing astronomical events happening in the sky. He observed a comet at the age of 6 and at the age of 9 he observed lunar eclipse. Let us learn today Kepler's laws of planetary motion. Kepler's laws give information and mathematical calculations about planetary motion. These laws provide information about orbit of planets around the sun. There are three Kepler laws related to planetary motion. These are: the first law is called law of orbit, second law is called law of areas, and the third law is called law of periods. First two laws of Kepler, that is law of orbit and law of areas, was published in 1609 and law of period was published in 1619. Kepler's first law, that is nothing but law of orbit. According to this Kepler's first law, all planets orbit in elliptical path around the sun, with the sun at one of the foci of the ellipse. According to law of orbits, sun is situated at one of the foci of the ellipse. That is, the sun is situated either at S or S dash. While a planet is orbiting around the sun, we observe there are the two positions. One position where the planet is closest to the sun, and another situation where the planet is farthest from the sun. Suppose a planet is revolving around the sun. Then there are the 2 points we need to discuss. The one is called aphelion and second one is called perihelion. The point P, which is closest to the Sun, so point P is called perihelion, and the point A is farthest from the Sun, and the point A is called aphelion. Thus, there are the 2 points, one is a perihelion and another is a aphelion. S is the Sun situated at one of the foci. During perihelion, the planets receives maximum energy from the Sun, and during aphelion, the planet receives minimum energy from the Sun. Thus, amount of energy received by revolving planet depends upon the position of perihelion and aphelion. According to Kepler, orbital speed of planet is not constant. It is minimum at aphelion and maximum at perihelion. And at other points, the orbital speed of planet is intermediate of aphelion and perihelion. Here we do observe orbiting planet moving slowly at aphelion and moving faster at perihelion. Let capital R be the radius of the Sun and the planet orbiting at a distance h from the surface of the Sun. So the distance from center of the planet to the center of the Sun equals to r plus h. Let m be the mass of the planet and capital M be the mass of the Sun. If the planet is orbiting around the Sun, then under balance condition, centripetal force equals to gravitational force. Therefore, let V naught be the orbital velocity. So centripetal force becomes mv square upon r plus h, and gravitational force becomes gmm upon r plus h whole square. From figure, r plus h equals to small r. Therefore, orbital velocity of revolving planet around the Sun is given by v naught equals to under root of gm upon r plus h. Therefore, orbital velocity of the revolving planet v naught equals to under root of gm upon r plus h, which is nothing but under root of gm upon small r, where small r equals to r plus h. Now, the orbital velocity at perihelion v naught p, p for perihelion, is equals to gm upon r1, and orbital velocity at aphelion v naught a equals to gm upon orbital velocity at p VOP equals to under root of gm upon r1 and VOA equals to under root of gm upon r2 greater than r1 implies V naught p greater than V naught a implies velocity of planet at perihelion faster than aphelion. From last discussion, we do understand that the orbital velocity of a planet is not constant. It changes from one point to another point. This helps us to understand Kepler's law of areas and Kepler's law of period. Suppose an orbiting planet moving from A to B in its path. While moving from A to B, it sweeps an area A1 where S is the Sun. S is the focus of elliptical orbit. Now, in another situation, suppose the planet is moving from C to D. While moving from C to D, the planet sweeps an area A2. Kepler's law of areas can be defined as follows. The line joining the planet and the Sun sweeps equal areas in equal interval of time. Now I am going to prove Kepler's law of areas. The proof of law of areas depends upon law of conservation of angular momentum. According to law of conservation of angular momentum of a rotating body. What is a rotating body here? Here is a rotating body is planet. So planet is rotating. So according to law of conservation of angular momentum of a rotating body will not change. That means angular momentum of the planet will not change unless and until no external torque acts on it. We know that while the planet is rotating, nobody is pushing it. It is rotating on its own due to centripetal and gravitational forces. The centripetal force is balanced by gravitational force, and because of this, the planet is rotating around the Sun in elliptical orbit. So the total angular momentum of the rotating planet will not change because no external force or external torque acting on the planet. This is nothing but law of conservation of angular momentum. Also, law of conservation of angular momentum valid only if the force is central force. Here we do observe that the gravitational force is towards the Sun. The gravitational force or gravitational pull due to the Sun on a planet is toward the center of the Sun. Thus, gravity is central force. Gravity is central force. And whenever the force is central force, law of conservation of angular momentum is valid. Now, let us assume Sun is at origin and the planet is having coordinates. Suppose the coordinates of the planet are x, y, z. Then the coordinates of origin are 0, 0, 0. We are assuming Sun as a origin and the planet having the coordinates x, y, z. Then the position vector of the planet is given by xi cap plus yj cap plus zk cap. So this is the position vector of the planet orbiting around the Sun. Let vector p be the component of momentum of the planet, and also vector p is perpendicular to vector r. That is, component of momentum of the planet is perpendicular to position vector r. Consider a planet is moving from point A to point B and covering an arc AYB and sweeping an area of delta A1. Let vector be the linear velocity vector of the planet. Delta t equals to time taken to travel arc AYB. For small interval of time, that is, the planet is moving from A to B in a very small time, that is a short interval of time, then arc AYB is almost a straight line. Since vector delta A1 is a vector space and the region shaded, the region swept by the planet during the small interval of time is almost triangular. Therefore, the area of this vector space, that is the delta A1, can be obtained by using half into base into height. Therefore, delta A1 equals to half into vector r cross vector v delta t. Dividing both sides by delta t cancelled both in numerator and denominator. Then we get delta A upon delta t equals to half vector r cross vector v. Let us call it as a equation number 1. Since linear momentum equals to product of mass and velocity, therefore vector p equals to m into vector v. Therefore we get vector v equals to vector p upon m. Let us call it equation number 2. Putting 2 in equation 1, we get delta A upon delta t equals to half into vector r cross vector p upon m. On further simplification, we get delta A1 upon t equals to r cross vector p upon 2m. But vector r cross p equals to angular momentum. Let vector r cross p equals to vector L. Vector L nothing but angular momentum. Therefore, equation 4 becomes delta A1 upon delta t equals to vector L upon 2m. Let us call it as a equation number 5. But for central force, the angular momentum is conserved. Therefore, delta A1 upon delta T equals to constant. This implies during planetary motion, planets sweeps equal areas in equal intervals of time. On the basis of above discussion, now we can define Kepler's law of areas. The line joining the planet and the sun sweeps equal areas in equal interval of time. Kepler's law of periods. It is also called Kepler's third law. It tells how fast a planet moves around the sun, and it gives relationship between orbital periods of planets and length of semi-major axis of the orbits. According to law of periods, closer a planet to the sun travel faster than planets far from the sun. The Mercury is closer to the sun, so it travels faster compared to Venus, and Venus travels faster too compared to Earth, and Earth travels faster compared to Mars. Thus, a planet nearer to sun travels faster compared to the planets which are away from the sun. Mercury is closer to the sun. It has period of revolution around the sun equals to 88 days and orbital velocity of Mercury 47 kilometers per second. Venus having period of revolution around the sun 225 days and orbital velocity, that is the mean orbital velocity, equals to 35 kilometers per second. The speed of the orbital velocity of Venus has decreased compared to Mercury. Earth, the period of revolution around the sun about 365 days and mean orbital velocity is 30 kilometers per second. We do observe that the Earth has become little slower compared to Venus. For Mars, the period of revolution around the sun is about 687 days. There is a drastic change compared to the Earth, and mean orbital velocity for Mars is about 24 km per second. Thus, as we move away from the sun, the period of revolution of the planet keep on increasing and mean orbital velocity decreases. All this data can be calculated by using Kepler's law of periods. Now, the definition of law of periods: the square of the time period of revolution of a planet around the sun is directly proportional to the cube of the semi-major axis of the ellipse traced by the planet. Let capital T be the period of revolution of planet around the sun. R equals to length of semi-major axis. According to law of periods, T square proportional to R cube implies T square upon R cube equals to constant.